Hello again, hackers. Today we are not going to smash the stack with a long string. We are going to do something quieter. We are going to walk into a shop, buy something, and somehow make the shop pay us. Not with a race condition, not with a leaked address, not with a shell pay us. Not with a leaked address, not with a shell code, just with a number that became too large to remain itself. Before we zoom in on the bug, we need the crime scene. A real challenge gives us artifacts, source code, a compiled program, command output, maybe disassembly, maybe debugger state. The rule is simple, no floating, explanation detached from evidence. Every close-up we use today comes from somewhere, a file, a line number, a command, an address or a selected row in the disassembler. So first, let's lay the whole program on the table. The program has two products. The real flag costs $100,000. We only have 1,100, so that path is locked. But there is a cheaper product, the knockoff flag. The user enters a quantity. The program calculates the total cost. Then it checks, is the total cost less than or equal to our balance? If yes, subtract the cost from our balance. That sounds reasonable. But the bug is hiding in the phrase total cost. The program does not calculate with mathematical integers. It calculates with C, integers, and C integers have walls. A beginner sees this and thinks, if I buy more flags, the cost gets bigger. One flag, 900. Two flags, 1,800. Three flags, 2,700. Eventually, the price is too high, and the shop says no. That is true in school arithmetic. But a computer integer is not an endless number line, it is more like an odometer. When every digit is full, the next increment does not create a new digit, it rolls over, and in signed arithmetic, the other side of that rollover can look negative. On a common 32-bit signed integer, the values usually run from negative 2,147,483,648 up to positive 2,147,483,647. That top value is int max. As bits, it is 0 followed by 31 ones. The 0 at the front means positive. If arithmetic pushes the bit pattern past that edge, the top bit becomes 1, and in 2's complement, that same bit pattern is now read as negative. In C, signed overflow itself is undefined behavior. For this challenge, we explain the observed compiled behavior as 2's complement wrapping, then later show how sanitizers catch it. Now return to the shop. The vulnerable calculation is 900 times quantity. We choose a quantity that is positive because it has to pass the check number flags greater than 0. But we choose it so large that 900 times quantity does not fit inside a signed 32-bit integer. For example, 3 million fake flags. Mathematically, that should cost 2,700,000,000. But inside this 32-bit result, the lower bits are kept, the sign bit is set, and the result is interpreted as negative 1,594,967,296. The shop thinks the final cost is negative, then the next line becomes beautiful and terrible, balance equals balance minus total cost. Subtracting a negative cost is adding money, so the exploit is not type of big number because big numbers are funny. The exploit is a chain. 1. The input is accepted because it is positive. 2. Multiplication overflows. 3. The overflowed cost becomes negative. 4. The bounds check asks the wrong question. 5. The balance update subtracts the negative value. 6. The real flag check sees a balance greater than 100,000. The program is not confused at the end. It is perfectly obeying the bad arithmetic from the beginning. This is an integer vulnerability, not because integers are bad, because the program used an integer result as if it were trustworthy proof about reality. The source wanted to prove that the user can afford this purchase, but the program only proved that the wrapped-in value is less than the balance. Those are not the same statement. Most integer bugs are exactly this kind of mismatch. The programmer checks one world, but the CPU computes in another. Now we widen the lens. Signless bugs happen when the same bits are read with different rules. Take 0xFFFFF as unsigned, it is 4,294,967,295. As signed 32-bit 2's complement, it is -1. Same bits, different story. That is why signedness bugs feel haunted. The value did not change, the reader changed. Multiplication is not special. Addition can do the same thing. PicoCTF has a tiny challenge called toSum. The program adds two signed integers. If two positive numbers produce a negative result, the program knows the addition wrapped. So the classic input is 2,147,483,647 plus 1. In school arithmetic, that is 2,147,483,648. In a 32-bit signed interpretation, the wheel crosses the edge and lands on -2. 2,147,483,648. The sum did not become logically smaller. The container was too small. Overflow is crossing the ceiling. Underflow is crossing the floor. If an unsigned counter is 0 and you subtract 1, it does not become -1. Unsigned integers do not have negative values. So the wheel rolls backward from 0 to the maximum value. 0 minus 1 becomes uintmax. That can turn a tiny mistake into a huge length, a loop that never ends, or an index that points nowhere near where it was supposed to point. Another integer bug is truncation. That means a large value is moved into a smaller container. Imagine a 32-bit integer being stored into a 16-bit short. The high bits do not fit, so they are cut away. The program may think it validated a large number, then later the shortened value means something completely different. This is especially dangerous when the truncated value becomes negative, passes a bad check, and then gets converted back into a huge unsigned size. CWE839 gives this family of mistake. A value can become a negative short, pass a maximum only check, then become a huge unsigned copy size. A bound check needs two walls, a maximum wall and a minimum wall. Many vulnerable checks only ask, is this value too big? But they forget to ask, is this value negative? That is how negative indexes happen. That is how negative lengths happen. That is how a value can look safe to the check, then become dangerous to the function that receives it. The right shape is not just x less than or equal to max. It is 0 less than or equal to x, and x less than or equal to max. Now we reach one of the most common dangerous shapes. A signed length enters the program. Len equals -1. The program checks if len is less than or equal to 512. That passes because -1 is definitely less than 512. Then the program calls something like memcopy, and memcopy does not take an int length. It takes a size t, an unsigned size, so -1 becomes a huge positive number. Suddenly a check that looked safe becomes a request to copy nearly everything. CWE195 describes this signed to untimed conversion failure. Now take the flag shop formula, price times quantity. Replace price with element size. Replace quantity with element count. Now it says size of element times count. That result is used to allocate memory. If the multiplication overflows, the program allocates a small buffer, but the rest of the program still believes the original large count. So allocation uses the wrapped number, while the right loop uses the real number. That gap is the vulnerability. This is the heap version of the shop bug. In the shop, overflow created fake money. On the heap, overflow creates fake space. Search INT30C examples warn that unsigned multiplication wrap in allocation size calculations can allocate insufficient memory. CWE190 notes that too little memory can make integer overflow primary to buffer overflow. This is why integer bugs matter in exploitation. They often begin as logic bugs, no crash, no obvious overwrite, just a wrong number, but then that wrong number becomes a memory boundary. Once the memory boundary is wrong, a normal write becomes an out-of-bounds write. Integer overflow into undersized allocation. Undersized allocation into heap overflow. Heap overflow into corrupted metadata, overwritten pointers, or changed program state. The first bug is arithmetic. The final consequence is memory corruption. Integer overflow can also happen before an array access. Imagine the program checks index plus length less than or equal to buffer size. That sounds fine. But if index plus length wraps around, the sum becomes small again. The check passes, then the program uses the original index and length to read or write. This is index wraparound. The value took a secret lap around the integer wheel before the guard saw it. The same idea exists with pointers. A pointer is an address. An offset is a number added to that address. If the offset calculation overflows or if base plus length crosses the address boundary, the resulting pointer may appear to be inside a safe region even though the intended range was outside it. This is why integer values used in pointer arithmetic are security sensitive. An offset is not just a number. It is a future address. Check the offset before addition. Check base less than or equal to end. Check length less than or equal to object size minus offset. One more trap. Not every integer type has the same width on every architecture. On many 64-bit systems, pointers and size t are 64 bits, but int often remains 32 bits. On LP64 systems, long and pointers are 64 bits. On LLP64 systems used by Windows, long stays 32 bits, while pointers are 64 bits. So code that seems safe on one target can become suspicious on another. A cast from size t down to int, a length stored in short, a pointer difference stored in the wrong type. These are places where the program may silently throw away bits. Source code says total cost equals 900 times number flags. But the CPU does not know flags, it knows registers, it knows multiplication, it knows that a register has a fixed width. So in this local reconstruction, we compile the supplied source and open the disassembly. The multiply instruction is at address 0, x40062D. It is integer multiply ex x ex 0x384. The immediate 0x384 is 900. EAX holds the low 32-bit result, and the program stores it as total cost. That is the bridge from C to silicon. We also attempted the optional WeBSAM build. The host linker is missing its libopsam runtime, so there is no sanitizer transcript here. We showed that limitation. Instead of making one up, the fix is not use a bigger integer and pray. Bigger containers only move the wall farther away. The fix is validated before the operation that can overflow. For flagshot, ask, is the quantity positive? Is the quantity small enough that 900 times quantity fits? Then calculate, then compare, or use check, arithmetic. In modern C, C23 adds checked integer helpers. Many compilers also have overflow built-ins. The important idea is the same. Make overflow a branch, not a surprise. The input range gate comes before multiplication. The affordability gate comes after a successful calculation. When you audit C or C++ code, look for integers that become decisions. Not every integer matters equally. Dangerous ones are sizes, lengths, counts, indexes, offsets, allocation sizes, loop bounds, pointer arithmetic, And security checks. User input touches one of these values, trace it. What type is it? How wide is it? Is it signed? Does it get cast? Is it added? Is it multiplied? Is it checked before or after the operation? Most importantly, is the checked value the same value that is later used? If allocation checks one number and copying uses another, the exploit lives in the gap. Integer vulnerabilities are strange because they often begin without memory corruption. The program just believes a number. But in low-level code, numbers become boundaries. Boundaries become buffers. Buffers become control. In Flagshop, the number made us rich. In real programs, the same pattern can make a buffer too small, a copy too large, an index negative, or a pointer wrap around the edge of memory. So when you see arithmetic near memory, slow down. Ask what world the program is checking, the mathematical world or the machine world, because the exploit usually begins in the difference. Until next time, hackers.